Yeah.
Okay, so today we're going to look at our last model for finding volumes. It does not involve revolution. Kind of. The math is easy. Getting to that point is a little bit difficult. The visualization is a little tricky too. So I'm going to go slow and try to explain things, and as opposed to not explaining things. And then we'll see what we can do with that. Okay, so let's start with a little drawing and some visualization skills. Okay. Let's suppose I take a rectangle. Okay. Two-dimensional surface of a rectangle. And I stack on top of that rectangle squares. So here would be my first square. Now I know what you're thinking. That's not a square. But again, we're talking about 3 dimensions, so this thing is sticking outside of the board. It would look like this. That big fat edge there would be the same thing as the big fat edge there. So let's take a moment to digest that. You got it?
No.
Yeah.
Could you use like the tissue box or something as an example? Like pointing. I don't get it.
I don't want to use the tissue box as an example because I need you to get this in order to be able to do the homework. So I take a base. I happen to choose, I happen to choose a base that's a rectangle, and I stack squares on top of it. And as I continue to stack squares on top of it, et cetera, what shape will I get? And we'll get a prism, right, that looks like this. Yes or no?
Just a bunch of
Oh,
squares
so,
in it, yeah.
so if you think about
So again, remember, these are sticking, these guys here are sticking out of the board at you.
Use the loaf of bread analogy.
so
that's
if
a
you
good one.
think about like a slice of bread is a square,
Yeah.
Bingo.
and you just like
Yeah,
okay.
slice.
Okay, okay,
Yeah.
good. All right, let's change it.
So
Let's start with a,
what's the width of the square?
I can't think of it.
doesn't matter.
Doesn't matter.
Let's start with another rectangle. And instead of stacking squares on top of it, let's stack
Try.
equilateral triangles.
So you're gonna do
Okay.
triangular.
So there's my equilateral triangle. Notice that that picture looks identical to the last picture. So I need to do a little sidebar over here to show you that I'm actually stacking equilateral triangles on top of that puppy. You with me? Good. What do I get?
Triangular prism.
Triangular prism. Okay, no problem. So we're taking two-dimensional objects, putting a whole bunch of them together. Bingo. We get a three-dimensional figure. So what can we change? Okay. Last example, and then we'll get into the slideshow. What if instead of having a rectangular base, I have a circular base?
Oh. What did you stack?
And so, what do we want to stack on here? Let's do squares again. So I'll take squares, put a square on there. And since we can't tell what that is, I'll draw it over here on the side. The fat edge down here shows you that that's the fat edge there.
So
Great question, Sam. Say that again. Are they all the same?
no,
Why?
because the circle has different diameter. Oh, well, there's only one diameter, but from one edge of the circle to another, it's not all the same.
Right. If I move over to the right, I'm going to have a bigger square. If I move over to the left, I get a smaller square. What's going to happen as I get really close to that point?
Infinity small.
Yeah. Okay, so now this will be the fun part. Try to visualize in your mind, as opposed to visualizing somewhere else. That made no sense. What is that thing going to look like when you...
The sphere.
Take your head down, please. Thanks. You put it right back up.
Left.
Hey! Take your hood off! Don't pretend you don't hear me! He's gonna go far in life.
I thought you were just gonna run him down, honestly.
I'm gonna tackle him.
That's what, I kid
That'd
that
be
way.
awesome.
Mr. Myers in our Phil Lit class the other day, he just chased him down the hallway.
Okay, so we build that three-dimensional model by sticking squares up on top of it, and you notice that we've already talked about the fact that the square is going to change size. The biggest square is going to be where the diameter is. The smallest square is going to be over here on the far side. What does that three-dimensional model look like? There's no answer to that, just wait. I'll show you. Okay.
Is it wonky looking, or is it like an?
How do you define wonky?
Is it defined?
Are you wonky looking?
Yeah.
Okay.
So does it look like me?
It looks just, if that's how we define
That's what
wonky.
wonky looks
Yeah,
like.
then we-
Mr. E, who drew the dry erase artistry over there?
I'm not sure.
100%.
That Batman is insane.
Okay, so the method we're going to use is called cross sections. It's called cross sections because we're building figures out of cross sections. In this case, there's two things we need to know. We need to know what shape the base is. We looked at rectangles and circles. We need to know what you're stacking on top of it. Those can be anything from squares to rectangles to equilateral triangles to semicircles. All kinds of fun things.
They're all gonna be the same height though, right?
Nope.
No, because they're squares.
That's it. In case you missed that, got one thing to worry about today.
Might be right here.
There you go. Find the volume using cross sections. Like I said, the math is easy. In fact, the formula is ridiculously easy. It's getting to that point that's going to be the difficulty. Okay, so here we go. Blah, blah, blah. This is what we already talked about. Let's go right to the sketch pad so that you, for those of you that are challenged visually, can see what this puppy looks like.
I thought you were just gonna say for those of you who are challenged.
So here's the circle. And then we want to get a three-dimensional thing, so I'm gonna make it all kind of crazy. So we got that. Whoa, that's a little too far. There we go. So we got that 3D thing going on now. And I forgot which one this is. I think this is squares. Yeah, squares. So there's 4 examples of squares I can stack up on top of that thing, and notice that they change shape as you get closer to the edge of the circle. When you take all of those things, and by the way, that there it is in 2D, there it is in 3D.
Oh, is it?
If you take all of those squares, because this is calculus, we should be able to add up all those squares. It does something like that. So it starts at 0, gets the biggest right there at the point that's the diameter, and then shrinks back to 0.
Looks like
So now I'll show you what that thing looks like.
That's wonky.
That would be wonky. So this edge out in front would still be curved. In fact, if you look at this thing from the top, it would look like a cylinder. It's just got this curved surface over the top of it. I don't know if this is going to make it blow up, but oh, there you go. Yeah. So there it is from the top. There it is on the side.
Can you stop it?
Yeah, I can stop it. Oh.
Rotate anytime.
Okay. Good. We're going to be able to find the volume of that thing in a little bit. Let's look at some different shapes, though. I've got a couple others I can show you. If I can get to the bottom here, which I probably can't. Hold on, I'm having some sizing issues here. I didn't want to do that. All right, maybe I'm not going to show you there's more on the bottom, but I can't get to it. Oh, there we go. Yes, I can. I lied. Okay, so now we can do equilateral triangles. Again, if we flatten it out to get that 3D thing going on, there's 4 of the equilateral triangles, all different sizes. And if we just sweep one of them, they get bigger as they get to the diameter, then they shrink, down to 0. And so that one looks similar to the last one we did. What shape are we getting with this black curve and the red diameter?
A parabola?
Nope. It's a semicircle. When everything is said and done, that puppy would be a semicircle.
Oh, never mind.
Whoa, that's.
It looks like it's
I don't know, it's like a, if you flip it on its back.
The black.
It looks like a.
Okay, so let's change the base now. Instead of using a circle as a base, we'll use a right triangle as a base, and we'll stack on top of that thing some semicircles. So we get the 3D thing going on again. That's what you'd get.
Oh, boy.
And then if you create solid, it basically just stacks a bunch of semicircles there, but what's changing is the size of the semicircles as you get closer to them.
It's a half.
It's kind of a half a cone, but it's a cone that's standing, it's not a typical cone that you're used to. It's a cone that doesn't have the center over the center of the circle.
It's a backwards horizon.
It's just laid out.
Sure.
Or it could be as laid
So that's triangles on triangles on top of triangles. Alright, stop this. Go back to here. What's the math look like? And there's a couple more examples. This is it. That's the formula right there. AX dx. All we need to know is the area of one of those shapes that we're stacking on top of the base. Just one.
How does it take care of all?
Well, we'll see. Now, it would be nice if that was that easy, but it's going to be a little trickier depending on the problem that we're looking at here. Quite a bit of geometry involved here. I think you can all find the area of a square or area of a rectangle. You might need a review on the area of an equilateral triangle, which I have for you. Circles shouldn't be a problem. Semicircles shouldn't be a problem.
That's half a
Okay, problem number 1. Let R be the region bounded by the graph of x equals y squared and x equals 9. Find the volume of the solid that has R as its base, and every cross section is a rectangle of height 2 perpendicular to the x-axis. There's a ton of information in there. First of all, what shape is the base?
rectangles.
Raise your hand, Cam, or stop talking. Lexi?
Rectangle.
No, that's incorrect.
It's a rectangle.
That is, nope,
It's a sideways parabola.
it's a sideways parabola, very good.
It's at the base.
We're gonna put all the pieces together. So we have a sideways parabola, and we're gonna stack on top of that sideways parabola rectangles.
Oh.
Unlike the last problem, I'm fixing the height of the rectangles, so they're all gonna be 2 centimeters high, 2 units high. As opposed to some of the pictures we saw on Sketchpad where the size changes, this one we're gonna start with something simple. So first things first, we get a picture. This is the region I'm gonna use. It goes from 0 to 9, because it says that up here, x equals y squared, out to 9. And we're going to stack a rectangle on top of that. The other thing that's important is noticing that it's perpendicular to the x-axis. So our rectangle is going to do something like that. And since that segment that I just drew doesn't look very much like a rectangle, we're also going to draw a sidebar here that has our rectangle. Shading is optional. The big honking, black line at the bottom, I use to represent the point that's, or the segment that's actually sitting on the base that we're talking about. The hardest thing about this particular problem is that. Where did that come from? Right.
Because, so the top, when it's at x equals 9, the top of it, the y value is root x, and that's just doubled when you go down to the bottom, so it's 2 root x.
Perfect. Does it have to be at x equals 9?
Yeah.
In other words, is that also the square root of x?
I'm not sure.
Anybody else?
Doesn't matter. It's
Doesn't
just
matter,
top- It's
right.
just top minus bottom, right?
Okay. And then as he mentioned, this is symmetric, so this would also be the square root of x. At x equals 9, we would know that distance, we'd have 3. And this would be 9. But we want to look for, again, just like all the other problems we did, any representative it's not even a segment that I put on this board, we want to be able to express the distance there. And that distance will be 2x. What's different in this problem than a lot of the other problems you're going to do is the height of this rectangle is fixed. Later on, when we start looking at squares and semicircles and stuff, that height will change depending on where you choose to put your rectangle. Okay, but this one is always going to be 2 because it says that in the problem. Therefore, what's the area of this rectangle? And I'm taking rectangles from where to where? Abby?
0 to 9?
0 to 9. That's all the hard part. Now we put it together. 0 to 9 of the area of this thing, 4 times the square root of x, and we're working in terms of x, dx. Bring with that.
Can you just go over again how that's 2 root x?
If we take any point on this curve, okay, let's say that point here. I put it over here. I probably shouldn't have put it there. That's a little confusing. But if I put any point on that curve, that point is going to be x comma square root of x
Oh,
because of this.
oh, okay.
And as Brennan said, that represents that distance. We double it, we get the whole distance, 2 times square root of x. Problems? Questions?
So what accumulates for the differences in height? What,
There is no difference in height.
no, but when you do have a difference in height, what changes that?
You'll see. It's worked into the formula.
Does it have to do with the dx or no?
Say again?
Does it have to do with the dx?
No. Abby?
Never mind. Never mind. It clicked. Never mind.
You got it?
Yeah.
Beautiful. Anybody else? I'll leave the math to you. I'm sure that you can all work that out, right? Okay, good. X to the 1/2. Does anybody not? I mean, I had a professor in college who always did that, and I hated it.
What?
But the rest is left up to you. And I seem to be the only one that didn't get it. So
Could you pick that up there?
Let's see.
the other stuff,
Yeah,
I just erased it.
Oh.
I can put it back in there though.
there's another step.
Oh wait, maybe hold on. I didn't just draw a dot. Oh, there you go.
It changed forms.
It's in the PowerPoint.
Handwriting recognition. All right, what do you want to change? Trig is not the answer, by the way.
Height.
Height, we could make the height variable. We could change the shape of the base. We could change the shape of the figure that's stacked up on top of it. Rectangles are kind of boring. Nobody really cares about that parabola. By the way, can you visualize what this shape would look like when you were done? It'd be a 3-dimensional parabola. Question?
Would it ever be asked to like where it gives us the volume and then we have to go backwards?
Oh, no. I don't, I wouldn't.
Take a direct.
I'll have to think about that. That could maybe be a good problem.
Why did you say that?
What did you say? How about an extra credit problem?
I'm sure give you full credit. Copyright.
Math is cool. This
Okay.
is-
Now we're gonna take circle,
Give Sam a good talk.
and this will actually find the volume of the thing that I had in the sketchpad sketch. We're gonna take a circular base that has a radius of 4, and we're gonna put a equilateral triangle on top of it, perpendicular to the y-axis. Something like that. And of course, to make our life easy, I'm gonna put that circle at the origin. Therefore, what's the formula of that circle? Sorry, what's the equation of that circle? Got it?
I don't know.
Did that just come out of you?
I'm not gonna say it out loud because I really, I don't. Come on,
X squared plus y squared equals 2 or 4?
No, the other way.
R squared.
The other way.
16.
16. Good. Okay. That wasn't so bad, was it? X squared plus y squared equals 16. How many people knew that? Be honest. How many people think maybe they could have? Okay, never mind.
Are you gonna, we're gonna have to draw the drawings? Or you?
Yeah, over on the side. Not on the figure itself. Nor will you have to draw the finished figure.
Okay. That's not-
That would take
Okay.
a period.
I was just gonna concern.
Can you get extra credit for that?
Sure. I'm gonna work in terms of x. So I solve that equation for x. Now, why am I working in terms of x? This doesn't follow the same rules that the revolutions followed, because notice I have a horizontal thingamajobber here. Normally that would mean we'd work in terms of y. Why? I'm working in terms of x because I need to know this distance. And the way I have my problem set up, that's an x distance. So I want to know the location of this point. This point is at the square root of I lied. I think we're going to work in terms of y. I don't know what I want to do yet. Well, I'll ask you, how long is that? How long is it in terms of x, first of all? Taylor,
4 minus x.
why 4 minus x?
Because it's in terms of x.
Where did the 4 come in though?
The radius.
So you want to, if what you're saying is true, you want to make that distance x? So this distance is 4 minus x?
Yeah.
Okay. Where is, whoops. Where is that point located? 2 answers. X comma what? Square root of 16 minus x squared. Or, where's that point located? Square root of 16 minus y squared, comma, y. Okay, you see what I did there? They're both correct depending on where you want to, when you want to talk, whether you want to talk in terms of x or in terms of y. That's a circle, so it doesn't necessarily matter which way we want to work. We can work in terms of x, we can work in terms of y. I don't remember what I did in this problem. Question?
Well, I was just gonna say, since the one that's actually like in the PowerPoint is perpendicular to the x-axis, wouldn't that mean that we should work in terms of x?
Doesn't matter. Again, I don't remember what I did. I probably worked in terms of y, but we'll find out in about 2 clicks.
So is that the hard part, getting the like your points from your equation?
Getting everything set up is the hard part. So the equation is just the absolute, oh, sorry, what is that squiggly thing? Integral of the area of that thing. And that thing in this particular case happens to be that equilateral triangle. Okay, so it looks like I did work in terms of y in this case. That's 2 times that because of the same reason that Brendan explained before in the parabola. It's twice the distance. I want to know the whole distance. Okay, now the fun part. Who remembers the equation of an equilateral triangle from geometry?
S squared root 3/4.
Woo! Oh, 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 oh. Somebody brought their big boy pants today. Well done, sir. S squared squared root 3/4. You all remember that, right?
Oh, yeah.
I didn't take geometry.
Let's move on.
It was a long time.
In this case, S would be that. S is the length of one side of the triangle. So the area of that triangle, in terms of Y, is that mess. Which actually simplifies pretty nicely.
The square root squared.
What's the square root of anything squared?
That number is.
So we get 4 times the quantity 16 minus y squared times the square root of 3 all over 4. It's not pretty, but it's workable. We're taking we're taking triangles from where to where?
-4 to 4.
Or
0 to 8.
-4 to 4, that's what he said. Or
-4 to 4 y-wise. If you put everything in front of that.
you develop a stutter.
Y-wise.
Oh, in terms of y.
Yeah, from -4y.
Uh-huh. Y-wise. As opposed to x-wise.
X opposed to X.
Uh-huh. In the way I have this set up, we would go from -4 to 4. How else could I do it though?
-4 to 0 multiplied by 2.
Bingo. -4 to 0 divided by 2. Sorry, or 0 to 4 multiplied by 2, not divided by 2. That's a silly statement. Was that too big of a jump there?
Yeah.
I get it now. Now I see the answer. Oh, yeah.
2 squared is 4. There's a 4 in the denominator. I canceled that. Square root of 3 times that mess inside. Gives you the area. For these problems, that's the hard part. Finding the area of the shape. Especially depending on some of the shapes you get stuck with, like an equilateral triangle. Rectangle's not that bad. Equilateral triangle's a little trickier. And as we talked about then, plug into an integral. I chose to go from -4 to 4. I probably like John's idea better, going from 0 to 4, because a lot of times when you plug in 0, everything will cancel out. I don't necessarily know if that's the case here. It will be actually, because we'll get 16y minus 1/3 y squared, or y cubed. But again, it's entirely up to you. Yes?
Is this where spheres are made up of
Oh, we'll get there.
equilateral triangles?
We'll get there.
I've
Hold
been
on.
waiting for that since 8th grade mystery.
Oh, happy day.
Because I remember you told me that, and I'm like, there's no way. There's just no way.
Right, you thought I lied to you.
Yeah.
Uh-huh.
I thought you were making fun.
Well, haven't you already figured out that you get spheres by
But infinitely.
revolving a semicircle?
Mhm. But I want to see how many times you got to do it. What's infinity, right?
Once.
Well, stacking triangles
Oh, stacking triangles?
to make a sphere.
No, you would stack semicircles
Really? I thought you stacked.
and then double it.
Oh, I thought the area or the surface area of a sphere was made up of equilateral triangles. That's where the
The big
4/3 by.
I see where you're going. All right, just hold on a second. So blah, 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 answer. Okay, great. Problems. Okay, good.
Millennium Falcon.
Get it? It's a cross section.
Oh!
No, I don't get it.
I didn't notice that.
I don't get it.
You don't know what a cross section is? Like a cross sectional diagram?
Oh, I get it.
Like the human body, you can slice or you can.
Oh. Well,
Like
what
the
is that?
Millennium
It's
Falcon.
What's the inside?
You can slice it.